Find the dimensions of the largest volume, the box that encompasses the largest space, if you're only allowed 64 square centimeters to build the box with. So let me draw a crude, very crude picture of a box. So what is the volume of this thing going to be? Well, x times y times z. So we need to maximize this volume under the constraint that the surface area is 64 square centimeters. Let's call the surface area A for area. Can you tell me what the surface area of a box with dimensions x, y, and z would be? So each face, there's two faces for each area. I don't think I said that right, but do you get the right idea? So for instance, this right-hand face will have the same area as its left-hand counterpart. You see that? And what will that area be? So x times z, and then 2 times that. 2 times x times z. And then for any other combination of products of either x, y, or z, there'll be 2 faces with that area. So you'll get 2 faces, front and back face of area y times z. So plus 2 times y times z. And what did I leave out? Plus 2 times x times y, right? The bottom face and the top face will have area x times y. And we know that that area is 64. Everybody see that? So you could think of this as a constraint equation. And it's good news that we're given this, otherwise we couldn't solve the problem. So what we know how to do is we know how to maximize a 2-input variable function, v of xy, let's say. But what we have for volume right now is 3 inputs, and we're not as good with 3 inputs yet. So what can we use this constraint equation for? We can use it to solve for z in terms of x and y and reduce the volume equation into just 2 variables, inputs, x and y. Okay, so that's what this constraint equation does for us. First of all, I could divide everything by 2, right? X times z plus y times z plus x times y equals 32. And then if I want to solve for z, I'm going to move the x times y to the other side and factor out the z, which gives me x plus y as a quantity times z equals 32 minus xy. Or would you agree z equals 32 minus xy over x plus y? Would you buy that for $1? Yeah? Okay, so then if you think of our volume equation that we want to maximize, v equals x times y times z, I'm just going to plug in what z equals in terms of x and y into that equation. And so if I do that, I get that the volume is equal to x times y times z, which is just this guy, 32 minus x, y over x plus y. Okay, so we want to maximize that volume. So I want to, as usual, find the critical point, or points, whatever the case may be. So to do that, well, there's different approaches here, but I'm going to go ahead and distribute out the x times y because I think it'll make it easier maybe. So I'm going to make the volume equal to 32xy on top minus x squared, y squared if I distribute out the x times y over x plus y. Is everything making sense so far? How do we find critical values? We take what kind of derivatives? The partial derivatives. Okay. So if I want to take the partial, let me get this back in the picture. If I want to take the partial of v with respect to x, I need lots of room here to do it. So v subscript x, I'm going to drop the function notation, just call it v subscript x. And I'm going to introduce an old friend, an old rule called the quotient rule that we haven't really talked about yet, right? Yeah, okay. The quotient rule, low d high minus high d low over low squared. And Carl's shaking his head. I don't like the quotient rule. The quotient rule is cool. Okay, so low d high. That means the low function is x plus y, right? So x plus y, and it's with respect to x, right? So d high, what's the derivative of the numerator with respect to x? 32y minus 2x y squared. That's low d high, right? Minus high, which is 32xy minus x squared y squared, d low. But what's the derivative of x plus y with respect to x? Well, I'll put the 1 there just so the notes are complete, right? And then all that over low squared. Low d high minus high d low over low squared. It's almost fun to say. It's almost lyrical. So x plus y quantity squared. Right? All right. So obviously this is an ugly quantity, and I'm going to have to set it equal to 0 eventually, right? I'm going to want to simplify it so I can actually solve it. So how can I do that? Well, I'll show you. First of all, maybe there's an easier way, I don't know, but I'm just going to distribute out the x plus y here. Let's see. If I do that, then what would I get? So first outer inner last, 32xy, right, for the first. The outer would give me what? X distributed to the last term minus 2x squared y squared. That's the outer. Then the inner would give me what? Plus 32y squared. And the last would give me minus 2xy cubed. Looks really bad, but it's going to get a little bit better. Let me distribute the negative. Minus 32xy plus x squared y squared. And then that's all over that denominator. X plus y quantity squared. Now, do we have some cancellation here? 32xy minus 32xy makes 0. Anything else?
Yeah, 32y squared.
32y, no.
Oh, wait, what?
We do have like terms here, right? A negative x squared y squared plus x squared y squared gives me, it doesn't go away, but it gives me, at least I can combine them, negative x squared y squared. So we took care of that at least. Let me cross it out just to indicate we took care of it. And then what's left? Plus 32y squared minus 2xy cubed. Anything left? I think that's it. This isn't near as bad as it looks, and I'll show you why. What can we factor out of the numerator? Each term contains a y squared. So we factor out a y squared, what's left in the numerator? Negative x squared. What else? Plus 32. What else? Minus 2xy. All over x plus y quantity squared. Okay. Ultimately, we're going to set this equal to 0. After we find v sub y, we're going to set both equal to 0 and solve that system of equations, right? But the thing is, we're not interested when y equals 0, right? Because that would produce a 0 volume when you take the volume formula v equals x times y times z, right? So obviously, we're not interested in a 0 volume. That's not going to produce a maximum, a 0 y dimension, because that's not going to produce a maximum volume. So we're not interested in this factor out here at all. When you set this equal to 0, the only thing this factor contributes is a solution of y equals 0. Likewise, the denominator never determines when an expression is equal to 0, right? So we're not interested in the denominator. So just this quantity in parentheses is what's going to get set equal to 0 ultimately. So it's not near as bad as it looks. Furthermore, because this formula up here is so symmetrical in terms of x and y, we can get the derivative with respect to y using symmetry and not have to go through this whole process. You just interchange the roles of x and y, right? Because down here they're interchangeable, and up here it's x times y and then minus x squared y squared. So if you interchange the roles of x and y with respect to what you did to find v sub x, you'll have v sub y. Okay, so here's what I mean. You know that this is v sub x, right? So v sub y, what's going to be on the outside when you find v sub y? Not y squared, but x squared. And then what would you have here? Minus y squared. 32 is not going to change. Minus 2yx, but that's the same as minus 2xy, right? Then you interchange x and y and x plus y quantity squared, same thing. Y plus x squared is x plus y squared. Do you believe that? If you believe that, we're in business. Okay, now to find our critical values, then we set the first partials equal to 0 and we solve this. But as previously discussed, the non-zero solutions will be given just when these factors in parentheses are equal to 0. So we end up with the equations negative x squared plus 32 minus 2xy equals 0, and negative y squared plus 32 minus 2xy equals 0. And then we can get even a little trickier with this. Anybody think of a good way to, I mean, yeah, you think this is an ugly system of equations, but is there a method of solving systems of equations that might come in handy here to get rid of some variables, to eliminate them? Big hint. Remember the elimination method? Let's subtract the bottom equation from the top equation. What do we get? We get negative x squared minus, or plus y squared actually, right? You got to distribute the negative. Negative x squared plus y squared, that doesn't go away, but doesn't 32 minus 32 go away? And then this will become plus 2xy, negative 2xy goes away, 0 minus 0, we get negative x squared plus y squared equals 0, or just y squared equals x squared. Now, normally this y squared equals x squared can be complicated because then y could equal negative x, right? Or y could equal x, but is that a complication we have to worry about here? Are the dimensions going to be negative? No. So if y squared equals x squared, and you know that y and x are positive, then y equals x. Agreed? Yeah. So it wasn't near as bad as it looked. Well, how does that help us, though? We need values for y and x. Well, let's go back up and see if there's anything we can plug in y and x to. Probably the best thing would be one of these. So could I plug in y right here? Let's try it, see what happens. Or y equals x, rather, right there. So that would give me what? Negative x squared plus 32 minus 2x squared equals 0. So just for completeness, I'll say I did this. I plugged this right in here because that's what y is equal to. Y is equal to x. Okay, so what do I get then? I get negative 3x squared is equal to negative 32, right? Or x squared is equal to negative 32 over negative 3, which is 32 thirds. Agreed? Or x is equal to, do I worry about a plus or minus in front of the square root? No, not in this case. In other cases, you will. Just the plus square root is all we're interested in. But of course, that's equal to y as well. So actually, I should have said this. Just same thing, right? And you're thinking z is the same thing, but we better prove it, right? So okay, stop me when we get to an expression we can use for z. Just say stop when we get there. It's up here somewhere. Got it? How about this guy? Right? Yeah. So 32 minus xy over x plus y. 32xy minus x squared y squared over x plus y is what I said, right? Let's make sure. 32. No, I wrote down the wrong one. I wrote down the wrong one. Let me fix that. 32 minus xy over x plus y. That looks better. So if you go ahead and plug this guy in here, and in here, and of course down there, and of course down there, you get some kind of challenging algebra if you're not awake. 32, okay, what happens if you multiply root 32 thirds times itself? You get minus root 30, or minus just 32 thirds on top. That's easy enough. And then on the bottom, well, it might be better to, well, I'll just plug it in as is, and then we might have to, it might be better to rationalize. Right? Which is, you add them together, you get two of them, right? So we get z is equal to 32 minus 32 thirds over 2 times root 32 thirds. Oh, how should I have written the top, by the way? Well, I think in terms of thirds, 32 would be what, 96 thirds? Minus 32 thirds would be 64 thirds, maybe? Would you buy that? Okay. And then if we, oh gosh, how do we want to do this? If we want to flip and multiply, let's see, we get 64 thirds. Okay, this 2 will, if you flip it, make it 1/2, will end up in the denominator, right? So times 2 down there. And then this will be, if you split up the radical, root 3 over root 32, correct? Okay. And then I don't know why I'm doing this algebra. I should make you guys do it. And then, so what is this, 32 thirds out front? 32 thirds, and then root 3 over 32, root 32. And then I just want to make sure, 32 thirds, oh gosh. Well, what is this guy rationalized to be? What can we pull out? Root 16, so 4 root 2, and that'll be 8. Man, we should just check the decimal, huh? So 8 root 3 over 3 rad 2. All right. Well, I want to prove to you it's the same, so this is why I never finish dealing with this kind of stuff. Okay. So root 2. Okay, so what do we get? So we get 8 root 6, I guess, over 3 times 4. That makes sense? So 2 root 6 over 3? That can't be right. Over 2 it should have been. Yeah. So this should have been 2, which would make that 4, which would make that 4. Okay. We'll have to fix that in editing. Now, that is the same as root 32 thirds. So you do get x, I'll let you verify, that's easy enough to verify that. I'll let you do that. And then, so you do get x equals y equals z. So the original problem said find the dimensions. The dimensions are root 32 thirds, and what are we in? Centimeters by root 32 thirds by root 32 thirds. It's a cube. Not surprising, right? But here's the thing, guys. In the homework, the box is going to be an open face, which changes this equation, right? You would only have one x times y in the equation when it's an open box. You'd only have one of these, right? And then it's not a cube anymore, okay? So you can't count on it being a cube. So the process that I showed you can still be useful to you as far as doing the homework. In the homework, you get a problem where you get to decide how big the box should be. You want to maximize the box that holds all your math awards. And so in the homework, you get to do that. And it's going to be similar to this example. Okay?